Welcome to the Quarkside Quantum Physics Podcast, an exploration of the fundamental structure of reality, where quantum laws govern matter, energy, and information. Here, uncertainty is a feature, not a flaw, and understanding begins at the smallest scales.
I want you to try something with me today. It's a little mental exercise to get us started.
Okay, I'm in.
I want you to close your eyes. Seriously, unless you are, currently operating heavy machinery or driving down the freeway, just close them for a second.
Safety first, please. But if you're safe, go for it.
Right, exactly. So picture your morning routine. You know the drill. You walk into that coffee shop you love.
Uh-huh. I can see it now.
You know the one I'm talking about? It's always just a little bit too loud. The grinder is going in the background, and it smells like roasted beans and maybe a hint of rain if it's a gloomy day.
Yeah.
You walk up to the counter and you order a latte.
The classic choice. Very good.
The classic. And the barista, who clearly takes their craft very, very seriously.
Oh, yeah, the one with the wax mustache and the denim apron.
That's the one, the whole vibe. They pour that steamed milk into the dark espresso. And they do that specific little wrist flick at the end. You know what I'm talking about.
The pour, it's mesmerizing to watch. It really is.
It is. And boom, there it is. A perfect tulip pattern in the foam. Crisp white lines against the dark coffee. It's symmetry. It's structure.
It's a little piece of art that you are about to destroy.
Exactly. It is beautiful. And it's fleeting.
So fleeting.
Right. Now, here is the experiment. Keep your eyes closed. Imagine taking that cup, it's hot in your hand, and just giving it a violent swirl.
Okay.
I mean, really shake it, agitate the whole thing. What happens to the tulip?
Well, obviously it's obliterated.
Right.
Instantly. You don't have a tulip anymore. You have a beige, frothy mess. The milk mixes with the coffee, the pattern dissolves, and you are left with a tasty but, visually boring drink.
Right. That is what our intuition tells us. That is what common sense tells us. That is what seeing the world every day tells us.
Things mix.
Things mix. Order turns into chaos. The tulip does not survive the swirl. It can't.
It's the law of the universe, or at least the law of the kitchen table.
What if I told you that in the quantum world, that logic just got completely flipped on its head?
And this is where we leave the kitchen table behind.
This is where it gets weird. Imagine you swirl that cup, you shake it, you tap it,
Yeah.
you disturb it, and you look down, and the tulip is still there.
Oh, wow.
Perfectly crisp.
Yeah.
Every petal defined. It refuses to mix. It refuses to blend. It just stays.
That is a perfect visualization of what we were talking about today. It sounds like magic or maybe a glitch in the simulation, right?
It does.
But it's actually a major breakthrough in physics known as statistical localization.
And this isn't science fiction. This isn't a theory from 50 years ago that we're digging up. This is coming directly from a study published literally yesterday, February 18th, 2026.
So it's brand new.
Brand new in the journal Nature Physics, and it's coming out of Duke University.
That's right. It's fresh research, and it is challenging some of our most fundamental assumptions about how matter behaves when you start looking really, really closely at it.
So today, that's our whole journey. We are going to unpack how a team of scientists use a quantum simulator, which, by the way, sounds like something straight out of a sci-fi movie,
It really does.
to essentially freeze the state of matter in a way that just shouldn't be possible.
And we need to be clear from the top. This isn't just a cool party trick for atoms. This isn't just, hey, look at this weird thing we found.
Yeah.
This is a big deal. It's potentially the key to solving one of the biggest bottlenecks in quantum computing, which is memory storage.
And if that wasn't enough, it might even help us understand the fundamental forces that hold the entire universe together.
It connects the very small to the very big. It's the bridge between the micro and the macro.
So grab your coffee, don't swirl it too hard, or maybe do, just to prove physics still works in your kitchen. And let's get into it.
Let's do it.
To understand why this frozen latte effect is so profoundly weird, we first have to understand what's supposed to happen. You mentioned earlier that the tulip disappearing is obvious. Why is that? What is the physics behind the beige mess?
So in the classical world, the world we live in, the world of coffee cups and tables and cars, we are governed by a concept called thermalization.
Thermalization. Okay, let's unpack that word. It sounds like it has something to do with heat.
It does, but it's really about equilibrium, about things evening out.
Right.
Think about dropping a single drop of dark blue ink into a glass of clear water.
Okay.
When you first drop it in, for that first split second, it's a tight little ball of color. It has a specific location, it's organized.
Right. You can point to it and say the ink is right there.
Exactly. But if you walk away and come back in, say 10 minutes, what do you see?
The water is just light blue. It's all spread out. You can't tell where the drop landed anymore. The blob is totally gone.
Precisely. The ink molecules have moved. They've gone from an area of high concentration, that initial drop, to an area of low concentration, the rest of the water. They've spread out until everything is equal.
Homogenized.
That is equilibrium, and that process is thermalization.
It's the same with temperature, right? That's the thermal part of the word.
Yes. The source material uses this great, simple example of a glass of ice water sitting on your kitchen table. You leave it there.
Right.
The heat from the room transfers to the glass, the ice melts, the water warms up. Eventually, the water, the glass, and the air in the room are all roughly the same temperature. They've reached equilibrium.
Everything wants to settle down. Everything wants to mix. It's like the universe has this deep-seated hatred of distinct things. It wants everything to be a lukewarm soup.
That's a pretty good way to put it. This is all rooted in energy transport. Energy moves. It flows from hot to cold, from organized to disorganized. In classical physics, systems naturally evolve toward this state of equilibrium.
It's predictable.
Okay.
It's what we see every single day. Honestly, it's kind of comforting, isn't it?
It is comforting. We know that if we put something hot next to something cold, they'll meet in the middle. It makes sense.
It's the arrow of time, in a way. You can't unmix the ink. You can't unmelt the ice.
No.
Once the latte is beige, you can't just shake it and get a perfect tulip back.
Exactly. It's an irreversible process. But
Here comes the but. I knew there was a but coming.
this is not always how things behave when you zoom in way, way into the atomic and subatomic scales. The quantum realm.
The quantum realm, where the rules are made up and the points don't matter. Or rather, the points matter a lot, but the rules are completely different from our intuition.
They are definitely different. At this scale, we encounter a phenomenon called localization.
Localization. Okay, so contrast that with thermalization for me. If thermalization is all about mixing and spreading out.
Localization is the opposite. It's about staying put. So if thermalization is the ink spreading out to fill the entire glass, localization is the ink drop hitting the water and just staying there.
Staying as a drop.
As a perfect, tight little blue sphere just suspended in the clear water.
Why? Is there something holding it there?
That's the weird part. Nothing is holding it. There are no walls keeping it there. It just doesn't spread.
It feels wrong. Like physically, viscerally wrong. My brain doesn't like that.
It feels very wrong. The source describes it as a situation where equilibrium spreading does not occur, even with nothing obviously preventing it.
So it's just stubborn. The ink is just refusing to participate in the laws of physics as we know them.
In a way, yes. The energy transport we talked about before, it just stops.
Yeah.
The system retains a memory of its original state, the ink drop, forever, instead of forgetting it and becoming a uniform mix.
It remembers where it started.
It remembers. It doesn't thermalize.
Okay, so that's the baseline weirdness of quantum localization. This isn't a brand new idea, right? Physicists have known about this concept for a little while.
Correct. We've known about standard localization. Often it's called Anderson localization for decades. It usually happens when there's a lot of disorder or sort of dirt in a system that ends up trapping the particles.
Like potholes in a road that stop traffic.
That's a great analogy, yeah. But this new paper from Duke is talking about something even more specific and frankly even weirder, isn't it? It's statistical localization.
Right, and that's the new discovery.
Yes. And to understand that, we really need to look at the experiment itself. Because they didn't just stumble upon this, they had to build a very, very complex machine to even see it.
This wasn't something they just found lying around in nature. They had to engineer it.
Precisely.
Let's talk about the team. We have Huanqin Lo. She's an assistant professor of electrical and computer engineering and physics at Duke.
And her colleagues, including Natalie Palko, who we'll definitely hear about later when we get to the theory side of things, it's a multidisciplinary effort, which is key here.
And they built something called a neutral atom quantum simulator. Now, when I hear simulator, I'm thinking of software. I'm thinking of like The Sims or a flight simulator on a PC.
Right.
But that's not what this is at all, is it?
No, not at all. This is a piece of hardware. The source material calls it a tabletop setup, but don't let that fool you into thinking it's simple. It's incredibly sophisticated.
So it's not code.
It's not code. We aren't simulating quantum mechanics using ones and zeros on a normal chip. We are using actual quantum objects to simulate other quantum objects.
So it's like using Legos to simulate how bricks work, rather than drawing bricks on a computer screen.
That's a perfect analogy. They are building a physical model of the physics they want to study.
Okay, so what are the Legos in this case? What are the actual building blocks?
They used atoms of rubidium.
Rubidium, element 37 on the periodic table.
That's the one. And they arranged these rubidium atoms into a one-dimensional chain. So I want you to imagine a string of pearls, but the pearls are individual atoms and they're floating in a vacuum.
Okay, a string of atomic pearls. But how do you keep an atom from just flying away? You can't exactly glue it down. Atoms are wiggly little things.
You use light. That's the amazing part. They used highly focused lasers, they're often called optical tweezers, to tightly control the position of each individual atom.
Optical tweezers.
Yeah, so you have this row of atoms, each one pinned in place by its own beam of light.
That is just... It always blows my mind that we can actually do that. Here, let me just hold this single atom for you with a flashlight. It sounds like something from Star Trek.
It really is remarkable technology. The source highlights this high degree of quantum engineering. They are manipulating the fundamental building blocks of matter with incredible, almost unbelievable precision.
But holding them in place is just step one.
Just step one. Step two is getting them to interact with each other.
Right, because a frozen line of atoms doesn't tell you much about mixing if they aren't even allowed to talk to each other.
Exactly. So they used another laser to excite the atom's electrons.
Excite them how? What does that mean, to excite an electron?
It means they use the laser's energy to push the electron into a higher energy state, a different orbit around the nucleus. When they do this, it causes the atom's behaviors to become intertwined.
Oh, okay.
In quantum terms, we're dealing with things like entanglement and interaction. The atoms stop acting like solitary individuals and they start acting like a collective system. Their fates are linked.
Okay, so we have a chain of rubidium atoms. They are pinned in place by lasers. They are excited and interacting with each other. This is the choreography that the source talks about.
Yes. The researchers set up this very specific initial state, and this is like drawing the tulip in the latte foam. They positioned everything perfectly, they set the energy levels just so, and then
they let it go.
They let it go, they let the system run.
They introduced the swirl.
Exactly. They allowed the engineered quantum evolution to happen. They released the atoms from that initial rigid control just enough to see what they would do. Would they thermalize? Would they mix?
Would the ink spread?
Yeah.
Would the tulip dissolve? That's the moment of truth.
That was the big question. And remember, in a normal system, or even in many quantum systems, you would absolutely expect interaction to lead to mixing. If I'm an excited atom and I bump into my neighbor, I transfer some energy. That neighbor bumps into the next one. Eventually, the energy is spread all over the place.
Everything should average out.
It should, but that's not what happened. No, they observed statistical localization.
So did the atoms mix like the coffee foam?
They did not. They stayed put, or rather, their state stayed put.
Almost all states are frozen. That's the quote from Honky and Low.
Almost all states are frozen. It's such a powerful and surprising statement. It defies the expectation of chaos.
I want to dig into how this is different from that normal localization you mentioned earlier. You said that was like potholes in the road. How is statistical localization different? Because the source makes a pretty specific and important distinction here.
This is a nuanced but really crucial point that Lowe makes in the paper. In the usual form of localization, that Anderson localization with the potholes, the properties of the system are pinned to a particular site.
Like a specific location in space. So atom A belongs in seat 1, atom B is in seat 2, and they can't move.
Right. Think of it like a traffic jam where every single car is stuck exactly where it is. Nothing moves at all. The disorder in the road, the potholes, prevents any movement. You look at the GPS, and that car is at the same coordinate for an hour.
Okay, total gridlock.
Yeah.
Every car for itself, stuck in place.
But in statistical localization, it's different. And this is the mind-bending part. The quote from the paper is, "Here, we see localization even though the conserved properties are rather spread out."
Spread out? But localized. That sounds like a contradiction. How can something be spread out and frozen at the same time?
It does sound like a paradox, doesn't it? Let's go back to the traffic jam analogy. In the old model, every car is stuck on the highway, completely alone.
Right.
In this new state, it's more like The cars might be able to drive around a little bit. Maybe they can swap lanes with the cars right next to them, but they can never leave their specific little group of cars. The group itself is frozen in terms of its overall configuration, even if there's some internal movement.
I think so. It's not that every single atom is glued to a specific coordinate. It's that the pattern, the relationship between the atoms is what's frozen.
Exactly. The overall state is preserved. The source explains that this was actually theorized back in 2020. The theory predicted that in certain quantum systems you would find subsets of quantum states are connected to each other and otherwise remain disjointed from all other quantum states.
Disjointed. That's a really key word here.
It is. Imagine a big cocktail party. Usually everyone mingles. After an hour, you've probably talked to a bunch of different people. The room has mixed. That's thermalization.
Okay. The room is buzzing, everyone is meeting new people, sharing information.
Exactly. In this system, it's like the party immediately splits into tiny separate cliques. The people in clique A talk to each other furiously, they're interacting, they're sharing energy, but only with each other. And they absolutely, completely ignore clique B, clique C, and clique D.
And clique B ignores everyone else too.
Everyone else. The room never mixes, the cliques remain disjointed, they form these little isolated islands.
So the system is fragmented, it shatters into pieces that don't communicate.
Yes. The technical term is a fragmented state space. And because these fragments don't talk to each other, the information that's contained within them doesn't leak out, doesn't dissipate into the rest of the system. It's protected.
So if we bring this all the way back to the latte, if my latte had statistical localization, the milk molecules might be dancing around with other milk molecules in their own little clique.
Right.
But they refuse to acknowledge the existence of the coffee molecules next to them.
Roughly speaking, yes, that's a great way to think about it. The tulip pattern is made of milk. If the milk molecules refuse to integrate with the coffee molecules, the tulip pattern stays. Even if you swirl the cup, the swirling moves the whole liquid around, but the internal separation remains. The cliques hold strong.
Lo calls this very, very weird, and I have to agree with her.
And she's right, too. She says, in this imaginary example, we would have expected the elements to mix together to reach equilibrium, and yet we still somehow see localization. It's a genuine surprise.
It's weird, but she also says it could be a powerful feature. And this brings us to the really important part of this whole discussion. The so what? Why do we care if atoms form cliques? Why does it matter if my hypothetical quantum latte doesn't mix?
Well, the first big application, and maybe the most immediate one, is the holy grail of modern technology, quantum computing.
Right. We hear about quantum computers all the time. They're supposed to be faster, smarter, solve impossible problems. But they're also incredibly fragile, aren't they? That's the catch.
Incredibly. The biggest problem, the single biggest obstacle in building a useful, large-scale quantum computer is something called decoherence.
Which is basically the system just falling apart.
It's the coffee mixing. It's thermalization. Quantum states, the qubits that do the computing, are ridiculously delicate. Any little bit of noise from the environment, a tiny change in temperature, a stray electromagnetic field, even just the simple passage of time, causes the quantum information to degrade.
It leaks out.
It leaks out. It thermalizes. It turns into that beige uniform mess. And when your information turns into a beige mess, you've lost your data. Your calculation is completely ruined.
So if you want a quantum computer to actually work for more than a fraction of a second, you need a way to keep the ink blue and the water clear. You need to preserve the state.
Precisely. You need a way to store information that is, and this is a quote from the paper, robust to unpredictable surroundings. You need a memory system that fights back against entropy.
And statistical localization offers a path to that.
It offers a very exciting pathway. Lo says its implications for robustly storing information in a quantum system are quite exciting. Think about it. If you can encode your data, your ones and zeros, into these frozen states, into these disjointed fragments,
then they're naturally protected.
They're naturally protected. The environment can't mess them up as easily because they refuse to mix. They refuse to listen to the outside noise.
Because they're in their own little clique, ignoring everyone else.
They're in their clique. The system naturally protects the information. It's like having a hard drive that automatically rejects any attempt to corrupt the files. It isolates the data in these little protective quantum bubbles.
That's huge. I mean, the source mentions that we're trying to move from these small simulators with a handful of qubits to larger quantum computers that harness thousands of them.
Right. And as you scale up, the noise problem gets exponentially worse. You have more atoms, more interactions, more chances for things to go wrong. Finding a mechanism that inherently resists mixing without you having to constantly fight to keep it separate with complicated error correction is a game changer.
It's like finding a material that's naturally fireproof instead of having to constantly spray it with a fire hose.
That's a perfect analogy. It builds the protection right into the fabric of the system.
So reason number one this matters. Better, more stable quantum memory. That alone would be enough to call this a major breakthrough. But there's a second reason this matters, and it gets a little more cosmic.
Yes. This is where it gets really fundamental. This connects to the work of Natalie Kalko, the assistant professor of physics at Duke, who was also on the study. It turns out, this experiment wasn't just about building a better memory chip, it was also simulating a very specific and very important kind of theory called lattice gauge theory.
Lattice gauge theory. That sounds intense. I feel like I need a degree just to say that sentence. What on earth is that?
Kalko describes it as the language that we use to describe 3 of the 4 fundamental forces in nature.
Okay, so just the building blocks of reality. No big deal.
Right.
Just the instruction manual for the universe.
Pretty much. We use these theories to understand the strong nuclear force, which holds atoms together, the weak nuclear force, which governs radioactive decay, and electromagnetism, everything from the nuclei of atoms to the environments inside particle colliders or, weird astrophysical anomalies.
So typically, physicists use massive supercomputers to crunch the numbers on these theories and make predictions.
They try to. But Kalko points out a major problem. Calculating the elaborate predictions embedded in these theories is exceedingly costly, if possible at all, on classical computers.
Why is that? Is the math just too hard? We have some unbelievably powerful supercomputers these days.
It's not just that it's hard, it's that it is exponentially complex. The number of variables you have to track just explodes. Trying to simulate the interaction of subatomic particles on a classical binary computer, one that uses just ones and zeros, is incredibly inefficient.
It's the wrong tool for the job.
It's like trying to simulate a hurricane using an abacus. You run out of computing power almost immediately.
So enter the quantum simulator.
Right. And this is the genius of it. Instead of trying to calculate what the atoms would do using a formula, they built a system out of atoms and watched what they did do.
It's the ultimate modeling tool. It's analog. It's like using a little wave pool to study how waves work instead of writing out a bunch of complex fluid dynamics equations.
Exactly. And here is the beautiful connection. It turns out that fragmented state spaces, those frozen, disjointed cliques we've been talking about, are a key feature of these gauge theories.
Oh, that's interesting. So the weirdness of the frozen latte isn't just a quirk of this one experiment. It's actually a feature of the fundamental laws of physics.
That's the punchline. The experiment successfully mimicked the math of the universe. The paper specifically says they used a U1 lattice gauge theory in a Rydberg simulator.
Okay, there's a lot of jargon in there.
Yes.
U1 lattice gauge theory.
I know, it's a mouthful. But essentially, it's a specific mathematical framework that describes how fields like electric fields interact with matter at a fundamental level. The truly significant thing is that they proved this type of simulator can act as a laboratory for subatomic physics.
We can study things that are too complex for our best supercomputers.
By creating them on a tabletop in a lab in North Carolina.
Kalko calls it an encouraging step toward a highly anticipated application of quantum computing for subatomic physics.
It opens a door that was closed. If we want to understand how quarks bind together to form protons and neutrons, or what happens inside the core of a neutron star, we might not be able to calculate it on a standard computer. But we might be able to build a model of it using rubidium atoms and lasers, observe the statistical localization, and say, aha, that's how it works.
It's really bridging two completely different worlds. You've got the engineers trying to build better computers for the future, and you've got the theoretical physicists trying to understand the fabric of reality itself, and this one experiment helps both of them at the same time.
That's the beauty of it. The same phenomenon, this bizarre refusal to mix, solves the engineer's very practical memory problem and validates the physicist's very abstract theory.
I want to step back and just look at the big picture here for a minute. We started with a simple cup of coffee. We ended up with the fundamental forces of the universe.
It's quite a trip, isn't it?
It really is. The source material mentions that this research could help probe questions about unusual material properties. What does that look like in the real world? What are we talking about here?
Well, we're entering an era of what people call novel quantum materials. We are discovering and creating states of matter that just don't exist in nature. Things like high-temperature superconductors, superfluids, maybe even time crystals.
Okay.
Statistical localization suggests there could be materials that exist in a perpetual state of non-equilibrium.
A material that never settles down. A material that stays excited forever.
Or a material that conducts energy in very specific choreographed ways rather than just letting it spread out randomly as heat. Imagine a wire that doesn't heat up when you pass electricity through it because the electrons refuse to thermalize with the metal lattice.
That would change electronics forever. No more overheating phones, no more fans in our laptops.
Potentially. It's speculative at this point, of course, but that's where this kind of basic research leads. It changes the rule book of what materials are even capable of doing.
And it all comes back to that initial surprise, the weirdness.
Lowe said it best in that quote. That is very, very weird, but it could be a powerful feature.
I love that attitude. In science, weird usually means we found something important. It's not a bug, it's a feature.
Weird is where the discovery is. If the experiment had done exactly what they expected, if the atoms had just mixed and thermalized like a cup of coffee, it would have been a boring day at the lab.
Right.
Yep, entropy still works. The second law of thermodynamics is safe. Let's go get lunch.
Physics still works as advertised. Everyone can go home now.
Exactly. But because it didn't mix, because the tulips stayed in the foam, they have a new tool, a new principle to work with.
It's fascinating to think about the scale of it all, too. The article talks about this spanning from nuclei all the way to astrophysical environments.
It shows the universality of physics, which is just a beautiful concept. The same fundamental rules that govern a tiny chain of rubidium atoms in a vacuum chamber also govern the massive forces inside stars. And by studying one, we learn about the other.
So let's recap for everyone who might still be picturing that coffee cup. What is the headline news here? What's the big takeaway?
The headline is, researchers at Duke University used a neutral atom quantum simulator to observe a phenomenon called statistical localization. This is a state where atoms, despite being able to interact, refuse to mix or reach thermal equilibrium. They stay frozen in their initial patterns.
And this is important for two main reasons, right?
Two main reasons. One, it suggests a way to build robust quantum memory that doesn't degrade over time, which is a huge step for quantum computing. And two, it provides a powerful new way to simulate and study the fundamental forces of nature, specifically lattice gauge theories, which are too hard for normal computers to handle.
It's a win-win. A practical win and a theoretical win.
It's a massive win, and it validates a theory from just a few years ago, proving that these fragmented states are real things you can build and observe.
It really challenges our perception of time and chaos, doesn't it? I mean, we are so used to the idea that things fall apart, that order degrades into disorder.
That's the second law of thermodynamics. Entropy always increases. Things fall apart. The center cannot hold. It's one of the most fundamental laws we have.
But here, in this little pocket of the quantum universe, entropy is. It's held at bay.
It's paused. The system finds a way to preserve its structure, to preserve its information against all odds.
It's like finding a sandcastle that the tide can't wash away.
That is a beautiful way to put it, a perfect analogy.
Before we wrap up, I just want to touch on the technology one more time, the lasers and lenses. The article has a picture. Obviously, you can't see it if you're listening, but it mentions a close-up look at tabletop quantum simulator setups, and that phrase, high degree of quantum engineering.
We really shouldn't gloss over that. This isn't just theory on a chalkboard. The ability to control individual atoms, to grab them with light, place them precisely where you want them, and then poke them with another laser to excite them with this level of precision is a monumental triumph of engineering.
It really is. We are manipulating the literal building blocks of matter like they are Legos. We are playing God with atoms in a very real, tangible way.
And we're doing it to test theories that describe the birth of the universe. There's something almost poetic about that.
So what's next for this team? The article mentions the evolution from small simulators to larger computers. Is that the next logical step?
That's the path. They've proven the principle with this one-dimensional chain of atoms. Now, can they scale it? Can they build a two-dimensional grid? Can they use this freezing technique to build a reliable memory bank for a 1,000 qubit computer?
And if they can, What does that unlock?
If they can, we are one giant step closer to practical, fault-tolerant quantum computing, which means better drug discovery, new material science, more accurate climate modeling, all the things we've been promised.
All starting from a frozen latte.
All starting from a frozen latte.
I want to leave everyone with something to think about. We spend our entire lives operating under the assumption that time moves forward and things mix. You spill the milk, it spreads. You break the glass, it shatters into a million pieces. But this research shows that at the very, very bottom of reality, there are exceptions. There are pockets of existence that refuse to mix.
It makes you wonder what else is down there.
It really does. If nature has a built-in mechanism to preserve information perfectly, to keep that tulip crisp against the relentless flow of chaos, what else might be frozen in the quantum fabric that we haven't found yet? Is there information stored in the universe using this exact mechanism that has been there since the beginning of time, just waiting for us to learn how to read it?
That is a profound question, a really profound question.
Something to mull over with your next cup of coffee.
Yeah.
Just, don't stare at the phone for too long. People might think you're up to something.
Indeed.
Thanks for joining us on this exploration of the quantum weirdness coming out of Duke. It's been a blast.
It's always a pleasure to freeze time with you.
See you next time.